Let's discuss functions. What is a function? A function from a set A to a set B is denoted with F, a colon, the set A, an arrow, the set B. That's just notation. But what a function is a rule that assigns each element A in the first set to a unique element which we call f of A in B. The set A here is the domain of your function. This is a very abstract concept, so let's see some concrete examples. So here's our first example. So let f of t be the population of the planet Earth in year t. So in this case, my domain is the set of all possible years, so all numbers, real numbers, and this is a function because every single year you could think of has some population of humans on Earth. Maybe that population is 0. If you stick in t equals negative a million, there were no humans on Earth, say. So f of negative a million would be 0. But every single year, every single element A in the set A has a unique population. That means that there's no one year that has two different populations. Every year has a single unique population. Let's see some more examples. Let G of R be the volume of a sphere of radius r. So if you give me different values of radius, I'll give you different volumes of the sphere. It's a function because every radius has a unique volume of the sphere. If you have a sphere radius 1, it has a single volume. How about h of p be the price of buying P jars of jelly. So if you go to the supermarket, you want to buy 1 jar of jelly, it costs a certain price. If you want to buy 2 jars of jelly, maybe there's a 2-for-1 discount or something, and so the price is different. I don't know. Okay, let's write down a function similar to those that we've seen more recently in this course. Maybe I could have y of x equals x squared plus 2x plus 1. So every value of x, every real number you can think of, has a unique output value. So these are examples of functions. You have an input and an output. Let's do another example. Let's suppose I say f of x is x minus the absolute value of x. I'd just like to do an example where this notation is made more clear. This notation says if you want the result of plugging in a certain value for x, we denote that by f parentheses and a. So this isn't the best notation because in mathematics we also sometimes use parentheses to denote multiplication, but it's what we've got. So if you plug in x equals 0, you get 0 minus the absolute value of 0, which is 0. If you plug in f of 6, you get 6 minus the absolute value of 6, which is 0. If you plug in negative 6, then you get negative 6 minus 6, which I believe is negative 12. So that was just a quick example showing you this notation where f of a denotes where a is sent by your function f. What is the domain of the function f of x is the square root of x squared plus 3x minus 10? So when I write down a function like this, the domain is the set of numbers that I'm allowed to plug in for x. The implied domain is all real numbers for which this expression makes sense. Now, we've discussed this in previous videos. When you have a square root function, I don't want a negative number under the square root. I don't want to get a complex number out. I want to get a real number. So the implied domain are values of x for which I'm not taking the square root of a negative number. So in other words, we need x squared plus 3x minus 10 to be a number that's bigger than or equal to 0. We've just been practicing with expressions like this. One way you can decide when this is bigger than or equal to 0 is to find interesting values on the number line that indicate regions that I could test for being positive or negative. So if you factor this function or you use a quadratic equation, you might find I get x plus 5 times x minus 2 is bigger than or equal to 0. So on my number line, I have interesting values at negative 5 and positive 2. So these create barriers that separate the number line into regions. Now I will test certain values. So if I plug in x equals 0 into this expression, I get negative 10. So here is the number 0, meaning in this region, the value of this function under the square root is equal to a negative number. If I plug in a number bigger than 2, like let's say I plug in 3, then this term is positive and this term is positive, so I get a positive number. And if I plug in a number smaller than negative 5, like negative 6, then this number is negative and this number is negative. When you multiply two negatives, you get a positive. Meaning, the domain are the places where I have positive regions in this sectioned number line. So, the domain is negative infinity up to negative 5. And I can also plug in numbers bigger than or equal to 2. So this was an example of a function where I had to think about the implied domain. What numbers were I able to plug in? I'd like to end with one more calculation involving a function, a calculation that you may see more frequently if you continue on to calculus. So how about this? Let f of x equal 1 over x squared. And my question is, can I simplify this kind of crazy calculation, f of a plus h minus f of a, all divided by h? Okay, well, to simplify, I will do this. So we have f of a plus h. That means wherever I see an x, I'm going to replace that with a plus h. So I have 1 over a plus h squared minus 1 over a squared, all divided by h. So I'm going to write that as multiplication by 1 over h. This can be simplified now. I'd like to get a common denominator to simplify this expression. So I'm going to multiply the first term, the first fraction, by a squared over a squared. So I get a squared over a squared times a plus h squared. The second term, I'm going to multiply the top and the bottom by a plus h squared to get the common denominator. So I get a plus h squared over a squared, a plus h squared, and that's still times 1 over h. Now I can actually subtract these two expressions. If you subtract the two expressions, expanding this term, multiplying it out, I'm not going to do every detail right here, but when you do that, you get negative 2ah plus h squared all over a squared, a plus h squared. Still have a 1 over h, and I guess you could finish simplifying by canceling the h here with an h in the numerator, and I will be ending up with 2a plus h over a squared, a plus h squared. So this was an example of doing a simplification with a function. This is a type of calculation you may see in calculus. Okay, wonderful.